Alright, we're now moving on to part 3, angular projectiles. Some things you need to know before we begin today. We are now no longer talking about just dropping things in the y direction. As you can see from the image, it's being moved in both the x and the y. So acceleration, just like before, acceleration in the x direction is 0. You can see all of the arrows are equally placed in magnitude. However, 9.8 is now going to be different for the y direction depending on which direction you're going. So if you'll see at the beginning, the red arrows are pointing upwards. That's because the acceleration is negative. It's slowing the object down as it reaches a higher and higher height. And then once it starts to drop, it begins to regain that acceleration. So it becomes positive again on the way back down. Velocity in the x direction is now something that you're going to have to calculate using SOHCAHTOA. So sine, cosine, or tangent. But VF and VI are still the same. Velocity in the y direction, again, this is something you're going to have to calculate using SOHCAHTOA, and we'll get to that in step 3 of our example. Let's go ahead and look at our example. A ball is launched at 4.5 meters per second at 66 degrees above the horizontal. It starts and lands at the same distance from the ground. What are the maximum height above its launch level and the flight time of the ball? So step 1, just like any time before, draw a diagram. We have our information on the left. So let's go ahead and just kind of draw a coordinate plane because we do have an angle. Here's our trajectory, our path of our projectile, and here's our angle theta. So there's our diagram. Pretty quick, pretty easy. Second step, just like always, note your knowns and your unknowns in that chart. So obviously the things that we know, we talked about acceleration in the x, we talked about acceleration in the y. We also know that we can't fill out anything else except for what we've been given. And like I mentioned, here's our diagram, our chart. And let's just take a look back at that diagram. So we started off at an angle, 4.5 meters per second at 66 degrees. We need to find the x direction for that velocity, and we need to find the y direction for that velocity. Okay, so we have an x and a y. So let's start with our y. Where is y located in comparison to our angle, theta, that red mark? Well, it's opposite, so we're going to use sine. So the sine of 66 degrees should be equal to y, that's our unknown, divided by the hypotenuse, which is 4.5. So if you'll go ahead and plug in 4.5 multiplied by the sine of 66, you should get roughly 4.1 meters per second. And that number will go into our VI. Now again, VF in y direction is likely to be different. So we're just going to hang tight on VF. We're going to do VI first. Alright, so let's go ahead and solve for the x velocity. VI and VF will be the same for this. So we're going to use cosine because x is adjacent to or beside our angle that we're looking at. So same step, same process, 4.5 multiplied by the cosine of 66. X should be roughly 1.8 meters per second. That will again go in the VI and the VF. Okay, so that's what we've gotten so far. Now we can go back and look at those same steps that we looked at for our horizontally launched problems. So the first step, of course, is solving for time. In this case, we're going to use the y direction. And we are going to pretend like we are dropping this object, or pretend like once it reaches the top, we're going to use VI or VF as 0. So let's say that we are throwing this object. We have 9.8 as our acceleration, 4.1 is our initial velocity. We have 0 as our final velocity because it does briefly stop at the top, and we're going to solve for t. Now, if you take a look at the image that you should have drawn, when we solve for start position to the top point, we're only solving for half the problem. So when you solve for t, when you do this calculation, you should get 0.42. That's not your final answer. your final answer should be that number doubled, because that's the time it takes to reach the maximum height from start. We need the entire time it takes. So the time to go from start to the maximum height, and then from the maximum height back down to the ending position. So we're going to multiply by 2, and that is the number that we plug in for time. Let's solve for distance now. Now that we have our time, we can solve in the x or the y direction, whichever. Let's start with the x direction. So we have velocity 1.8, we have time 0.84. Go ahead, plug in, solve. You should get roughly 1.51 meters as your x. We're going to do the same for y. We're going to use the VF squared formula in this case, just to make things a little bit nicer. So VF squared equals VI squared plus 2AY. Of course, that's our distance. Plug in. We're going to rearrange. We're going to solve for y, and you should roughly get 0.86 meters. And that'll go into your y position. Now, last step, final velocity. For the y direction, you can do this a number of ways. I'm just going to use the VF squared formula again. So VF squared equals 4.1 squared plus 2 times 9.8 times 0.86. VF, roughly get about 5.8. And of course, that will go into your VF slot. So this is your practice problem. There is an assignment in Edmodo for you that has some more examples that I want you to work through. Please make sure you bring any questions that you have to class tomorrow.